Suppose that single particle states B and J and M are initially occupied. And we operate on this state first with the annihilation operator Bj. Then we're going to have our state B, J and M are initially occupied, and we're going to operate on it with this annihilation operator here. And the result will be what we see over on the right with a minus sign, because we had to swap the J and M rows to get the J row to the bottom. So this operator acting on this determinant, we had to swap this down to the bottom before taking it off. That swap down to the bottom put a minus sign in here for us. Now let's operate with the creation operator for state K. So this is what we want to do. Here was our starting state. We were first operating on it with the annihilation operator Bj, and then we're going to operate on it with our creation operator Bk. Well, we know what the effect of Bj operating on all of this was. It was minus this determinant here. Now we're left operating with this operator, and that will give us a determinant with a row k filled in, but of course we had to swap that up from the bottom, and we had to make a sign change because of that row swap. So that has cancelled our minus sign here. So let's consider applying these same operators in the opposite order, starting now with the creation operator for state K. So here was our starting state. We're now operating with the creation operator for state K. That puts a row on the bottom with k's in it. We have to swap that once here. That gives us a minus sign. Applying the annihilation operator now for state J gives us this mathematical expression, our original state, which we first operated on with the creation operator for state K. We're now going to operate with the annihilation operator for state J. This here, with the minus sign, was the result of the creation operator operating on this, and now we're going to operate with the annihilation operator. Well, we see what's going to happen. We're going to have to swap this J row twice to get to the bottom. So we will get rid of the J row by swapping it twice to the bottom and taking it off and taking off the fourth column as well. But that was two swaps, so that's no sign change. So we're still left with this minus sign here. So in operating with the annihilation operator, two swaps were required to get it to the bottom, past the M and K rows. As before, we find an additional row swap is required with one order of operators rather than the other. So the result of this order here, first of all the annihilation operator, then the creation operator, is minus the result if we do this in the opposite order. In this second case here, as we showed, we ended up left with a minus sign. Hence, at least when operating on states when single particle state J is initially full and single particle state K is initially empty, we're going to get this kind of anti-commutation relation, just like the ones that we got for annihilation operators on their own or for creation operators on their own. Now, analogously to what happened when we had the creation operator, we're going to find now that if state J is initially empty, then both of these pairs of operators will lead to a zero result, because we'll have an annihilation operator for state J trying to act on a state where there's no particle in single particle state J. So these annihilation operators are going to give us zero-length vectors. And hence, the result of both of these taken together is also going to always give us a zero-length vector, so this is a zero operator, if you like. And similarly, if state K is initially full, then these operators, which are trying to create another particle in single particle state K, are going to lead to zero-length vectors. So, as long as states J and K are different states, this relation is universally true with the zero or zero operator on the right here. So the only special case we have to consider more carefully is, as we said, this one when J and K are the same state. Suppose that single particle state K is initially full. Then when we operate here with this creation operator on this total state here, because this state is occupied, the single particle state for K is already occupied, the result of this has to be a zero-length vector. The result of this operator operating in this state has to be a zero-length vector, and a zero-length vector operated on with another operator is still just a zero-length vector. So that's because the creation operator bk dagger operating in this state gives us a zero-length vector. For the other order of operators, bk dagger, bk, and operating on this state, well, the effect of this annihilation operator operating on this state does not give us a zero-length state because this state was occupied. The annihilation operator operating on this corresponds to swapping this to the bottom, which gives us a minus sign, taking off the right column, leaves us with this non-zero state here. And then we can use the creation operator to create a particle in state K that puts a row with K's in it in the bottom that we then swap up, so we get a minus sign cancellation here. So it's left as an exercise to repeat this derivation for the situation where the state K is initially empty. In both cases, the result is the same. One or other of the pairs returns the original state, and the other pair returns 0. Hence, we can say that this set of operators here is equivalent to actually an identity operator, which we tend to write just as 1 here. Putting this together with this relation, where we tended to write the right-hand side as 0, it's technically a 0 operator, we can write the anti-commutation relation for mixed annihilation and creation operators in this general form. So we have a Kronecker delta on the right. If you like, technically multiplying an identity operator, but we have the Kronecker delta on the right, and this is the complete anti-commutation relation for creation and annihilation operator pairs. Finally, we note that this pair of operators in this order is the Fermion number operator for the state K, which is something we can easily verify. That is, it will tell us the number of fermions occupying state K. If the state is initially empty, it will return the value 0 because the annihilation operator operating on that state with no particle in single particle state K will just return 0, or the zero-length vector. And if the state is initially full, it will return the value 1. The annihilation operator operating on the full state will turn it into the state with no particles in state K, and then the creation operator will turn it back into the state with 1 particle in state K. So we can formally write this, if we like, by analogy with what we had for the boson case as a number operator for this Fermion single particle state K.